All right, so we're going to pick up where we left off on Monday, talking about acyl derivatives, finish up this chapter. So this continues our discussion of chapters 18 and 19. And the part that we need to finish up is thinking about a few other nucleophiles. So the first thing we're going to talk about is a few acyl derivatives with hydride nucleophiles. And so if you remember, we talked about reductions of carbonyl compounds like ketones and aldehydes with, for instance, lithium aluminum hydride followed by acid. And remember, what we figured out is that lithium aluminum hydride really behaves as though we have an H- nucleophile. And so we can have reaction of that hydride at the carbonyl to give us reduction of the carbonyl by delivering that H- nucleophile. And then in the second step, we would just put on a proton of the O-, and so this allows us to make alcohols. So it turns out, because acyl derivatives have a carbonyl, we can do similar chemistry with carbonyl compounds. From a practical standpoint, this is mostly only done with 3 of the acyl derivatives that we talk about. So the first one I want to talk about is hydride reduction of carboxylic acids. And so this is what the reaction looks like. So if I take a carboxylic acid and I react that with lithium aluminum hydride, what I wind up doing is reducing the carbonyl compound all the way down to an alcohol. And so what I'll get out of this reaction is a primary alcohol, so effectively just erasing the presence of that carbonyl by delivering hydride to the carbonyl. And what we will see is that it turns out there's an intermediate of an aldehyde here, and we'll look at the mechanism in just a second. So that's the reaction. Let's look at how this thing works. Okay, so if we think about the mechanism, a couple of things can happen in this case. So you have to use an excess amount of the lithium aluminum hydride. Remember, it has this structure where we have 4 hydrogens attached to an aluminum. And so the first thing that happens actually is one of those hydrides acts as a base and pulls off that hydrogen on the carboxylic acid. And so what we'll get from that is carboxylate plus AlH3 plus H2 gas. Okay. The next thing that happens is that negatively charged oxygen can recoordinate with the aluminum, and that's going to be important because that's going to give us a reasonable leaving group. So we will get a species that looks like this. And so then what will happen at this point is another equivalent of the aluminum hydride will deliver its H- to the carbonyl, and we do the thing that carbonyls always do. We add a nucleophile. We go from the carbonyl compound to a tetrahedral intermediate. And then that will reform a carbonyl and spit out that aluminum as a leaving group. And so at that point, here's where we get the aldehyde intermediate which, as we know from the previous chapter, can react with additional aluminum hydride to do the reduction. And so what we end up with in that second step is the formation of an alkoxide, where now we have added 2 equivalents of H- to the carbonyl, and we get stuck there as the fully reduced thing until we stop the reaction by adding a protic quench, and that puts the proton back on the oxygen. And so that's how we wind up with alcohol all the way down, coming all the way from a carboxylic acid. And so in terms of examples, it's pretty straightforward. Doesn't really matter the structure of the carboxylic acid that I choose to employ. So I'll just do a couple of examples. So if I reduce either of these two with lithium aluminum hydride followed by H+, again, all I'm going to do in this case through the mechanism we just went through is end up removing the presence of that carbonyl through the sequence of events that we just talked about. So what I would get in this case is formation of the alcohol in both cases. So I would get the alcohol at the top, or I'd get benzyl alcohol here at the bottom. But again, this addition of H- nucleophiles is what allows us to reduce this these carboxylic acids all the way down to alcohols. Now, you have to use lithium aluminum hydride. If you recall back to the previous chapter, we saw another hydride reducing agent, sodium borohydride, but that one is not reactive enough to do this chemistry. So in this case, lithium aluminum hydride is required for the reduction of the acyl derivative. Okay, so that's the first one. We can reduce carboxylic acids all the way down to primary alcohols. Second reaction is related. This one is the reduction of esters. Again, we're going to use lithium aluminum hydride, and it should not be surprising to you that this is going to give us essentially the same outcome as reducing the carboxylic acid. So if I take a methyl ester, for instance, and I treat that material with lithium aluminum hydride followed by H+, I'm going to do similar things where I will reduce the carbonyl first down to an aldehyde and then down again to an alcohol. So what we end up with again is making primary alcohols out of the esters. And so if you take a look at the mechanism that we just drew for the carboxylic acid, this approach actually turns out to be a little bit more straightforward. So, because I don't have to worry about removing that proton that we had to pull off for the carboxylic acid. So if I want to think about how this might happen, that ester would see lithium aluminum hydride. Hydride would release from aluminum, go to the carbonyl. Again, we're going to do the things that carbonyls like to do, which is form a tetrahedral intermediate and then try to reform a carbonyl by losing the better of the two leaving groups. My choice here is to spit out OCH3 or to spit out H-. So OCH3 is a weaker base, and so I'll lose that OCH3. That leads me to my aldehyde intermediate, which, as we saw in the previous chapter of aldehyde and ketone chemistry, that's also going to be reducible with a hydride nucleophile. So that will then react, in fact, faster than the ester to reduce that compound all the way down to a primary alcohol. So I would get this alkoxide after the second hydride adds in, and then from there quench this reaction with that H+. That is there simply to put the proton back onto the negatively charged oxygen, and that's how we would arrive at primary alcohols from esters. So those two reactions, reduction of the primary, reduction of carboxylic acids and reductions of esters, will always give us primary alcohols by adding two H- nucleophiles. So we can actually write that down. Sorry, let me erase this. So carboxylic acids and esters react with lithium aluminum hydride to make primary alcohols. So we can do another example or two of this with the ester. So let's say I have this methyl ester, or let's say I have this ethyl ester. If I choose to reduce either one of these with lithium aluminum hydride, I'm just going to again add H- nucleophile twice. First to make the aldehyde intermediate, and then that will accept a second nucleophile to make the primary alcohol. So I will essentially end up erasing the presence of the carbonyl and always losing the alcohol component of the ester as the leaving group, right? That ends up going away. So the second answer would look like this. Okay? So I can easily reduce these esters and carboxylic acids all the way down to alcohols. Now, synthetic chemists have wondered, well, what if I don't want to go all the way down to the alcohol? What if I would like to stop at the aldehyde? So that's a reasonable question. How might we stop the reaction after adding only one H- to make aldehydes? Because that could be synthetically useful, because we've seen an awful lot of reactions we can do with aldehydes, and we're one oxidation state away from that with esters and carboxylic acid. So is there a way to do this? Well, it turns out the third reaction we're going to talk about today is what's called a partial reduction of esters. So we have to do esters in this case with a reagent called diisobutyl aluminum hydride. Or dibol for short. So dibol is a reagent that was invented for this purpose, actually. So it was actually designed to do what we're asking to do here. So how can we actually take something in the acyl derivative oxidation state and reduce it down to only the aldehyde ketone oxidation state by a partial reduction? So here's what that reaction looks like. And so let's take a look at just a simple ester like methyl acetate. So dibol, first let me show you the structure of dibol. Dibol has this structure. It has one hydride on it and these two bulky isobutyl groups. Okay? And you'll notice that unlike lithium aluminum hydride, which has 4 ligands and the aluminum is negative, this is a neutral aluminum species, so it's coordinatively unsaturated. It has an empty orbital, and that's going to become important in just a second. So we'll talk about actually why the presence of that empty orbital allows us to stop at the aldehyde. So here's what the reaction looks like. In the first step, we will add dibol. And importantly, we're going to do this reaction under very cold temperatures at minus 78 degrees C. There's nothing special about minus 78 C other than the fact that it's really, really cold. We get to that low temperature at minus 78 by mixing dry ice with acetone. So it's just an easy, very cold solution that we can make. And we're going to need that cold temperature to make this reaction work. And I'll explain that in just a second. But we'll mix the ester with diball at minus 78 to do the partial reduction, and then we'll quench that with acid in a second step. And the outcome of this reaction is going to be the partial reduction of the ester down to the aldehyde. Okay? So we stop here. We don't do further reduction. Actually, let me write that where the words aren't running together. Sorry. So we can stop here without further reduction. Okay? And so that is a challenge, right? Because the aldehyde turns out to be more reactive than the ester. So if it forms in the presence of a hydride reducing agent, it's going to reduce like a shot. So what we end up doing with this reaction is preventing the formation of the aldehyde in the presence of the reducing agent. So let's go through the mechanism of this reaction, see if we can understand what's happening. Okay, so because diball is coordinatively unsaturated, we can actually use the lone pair electrons that sit on the lone pair electrons that sit on the ester to coordinate with that aluminum. So they will add into the empty orbital on aluminum to form a complex between the ester and aluminum. And that's important because what that does is add an extra ligand to the aluminum, and it now makes that aluminum negative. And because that aluminum is negative, that makes this actually be a much more reactive hydride source. So after we form this Lewis acid, Lewis base complex, the aluminum is negative. That enhances the reactivity of that aluminum hydrogen bond. And so that bond will deliver the hydride to the carbonyl and reduce the carbonyl from the ester oxidation state down to a one step lower. And so here's what the product looks like from that initial step. And herein lies the really important part of the diball reaction. So I've delivered the H- nucleophile, and now what I have is the bond of that oxygen to aluminum, but I also have a lone pair electron on this OCH3 group, which can donate into that newly empty orbital on aluminum and stabilize this complex. So I get stuck here, and what I effectively have is a stabilized tetrahedral intermediate. And that's super important, right? Because if I have a stabilized tetrahedral intermediate, it can't form the aldehyde, which could then reduce further. So I get stuck here having only delivered one of the... So I get stuck at this point, and I've only delivered that one hydride to go from ester to aldehyde oxidation state, and then I get stuck at this tetrahedral intermediate. And that's where the reaction stops after step one. And so I hang out. As long as I keep this reaction cold, I can maintain that stabilized tetrahedral intermediate until I decide to quench this reaction with acid. And if I add acid, what I do then is I can actually promote the collapse of this tetrahedral intermediate down to the aldehyde. So I only reveal the aldehyde after I have destroyed any remaining diball. And so this allows me, if I keep the temperature cold enough, to go only one step in oxidation state down from the ester to the aldehyde oxidation state. Okay, and so that stabilized tetrahedral intermediate, that's really the most important part of this system. If I stabilize that tetrahedral intermediate, it can never form the aldehyde in the presence of diball to undergo further reduction. And again, the key to being able to do that is that this step needs to be done at very cold temperature, so that when we form that tetrahedral intermediate, we stop there and we don't go any further. All right, so if I want to think about some examples of this reaction, as far as solving these types of questions, pretty straightforward. So if I have an ester and I decide to react it with Dibol in the presence of, and then follow it by acid, so long as I run that reaction at -78C, I will deliver an H- nucleophile. I'll make a stabilized tetrahedral intermediate, and then I quench that with acid. The net result is that I'm going to end up reducing that ester down to an aldehyde, and I'll stop there at the aldehyde. I'll show you one more example. If I take an ester like this one, treat with Dibol, again at -78C, follow that up with H+, I'll deliver the one hydride nucleophile to the ester, make that tetrahedral intermediate, and then collapse that tetrahedral intermediate and destroy the remaining Dibol in the second step when I add acid. What that's going to do is lead me just to the aldehyde product. Okay? So that is how we can go about stopping part way through the reduction and isolating aldehydes from the carboxylic acid ester oxidation state. So we have to use esters, we have to use Dibol at cold temperatures. Okay? All right, so the last hydride reduction that I want to talk about in this chapter deals with hydride reductions of amides. So the reason these are important is that we actually turn out, this is a good way to synthesize amines. Okay, and so what this amounts to is a way in which we can remove a carbonyl from an amide. So if I take, for instance, this amide, I can react that with lithium aluminum hydride, followed by a little bit of H+. And what I will do in this case is end up removing the carbonyl, similar to what we did with the carboxylic acid. We end up adding hydrogens until we reduce the oxidation state down to the amine. Okay, I'm not going to worry about the mechanism here. It's similar to what we had seen before with the lithium aluminum hydride reductions, but suffice it to say, if I take an amide, treat it with lithium aluminum hydride, what I end up doing is losing that carbonyl oxygen and making amines. This is a common way to synthesize amines. So let's look at a few examples. So let's say, for instance, I had this amide. If I end up treating that with lithium aluminum hydride, followed by a little bit of H+, what I'm going to do there is effectively remove the carbonyl, and that's going to give me, in this case, because I have a secondary amide, I'm going to make a secondary amine product. So I get this product where I effectively remove the presence of that carbonyl. And then if we think of a separate example where, I don't know, let's say we have a tertiary amide. If I do that same reaction, again, the result is going to be to remove the presence of that carbonyl, go from an amide reduced all the way down to an amine. So that's a really common way, along with the reductive amination of aldehydes and ketones, that's a really common way to make amines. It's just to do a hydride reduction of amides. Okay. All right, the last thing that I need to talk about with this chapter deals with adding carbon nucleophiles. Boy, could I write that worse? Let me clean this up a little bit. Uh-oh. So the last part we're going to talk about here are using carbon nucleophiles. And there are two that we're going to look at. So the most important one by far is adding things like Grignard reagents to esters. Okay, and so here's what that reaction looks like. If I take an ester, like this one, the way this reaction would take place is I would use some kind of Grignard reagent. Let's see, like ethyl magnesium bromide. And importantly, I really have to use two equivalents. That's very important. I have to use two equivalents of this reagent to get a productive reaction, and I'll tell you a little bit about why that is in just a second. And then we'll follow that up, as always, with a little bit of H+. And what we will always get out of this Grignard addition reaction to an ester, we will always, always, always make tertiary alcohols. Okay? And so the alcohol product of this one would be reduction of that carbonyl down to an alcohol that has happened by adding two equivalents of the ethyl group. Okay? So we'll end up reacting the Grignard reagent with the carbonyl compound to make a tetrahedral intermediate that will reform the carbonyl, and then we'll add in another one. And so let's look carefully at the mechanism here, and then we will try to understand why we must use two equivalents to have a productive, high-yielding reaction. All right, so here's the mechanism. So that ester, when it sees a Grignard reagent, hopefully you remember that when we see a Grignard reagent, we really treat it as though we have a carbanion, right? So we have a CH2 minus there. And that's a pretty potent nucleophile, so that guy will add to the carbonyl and give those electrons to oxygen, and that will lead me to a tetrahedral intermediate. And so I think everybody hopefully would expect that as the first outcome of this reaction, just like we've done with reactions of all of the carbonyl compounds we've discussed. So I would get a tetrahedral intermediate, but this particular tetrahedral intermediate still has this OCH3 leaving group. And so I can, in this case, reform a carbonyl and lose a leaving group. And that will lead me to a product, initial product, which is a ketone, right? The reason that we have to add two equivalents of this reaction is that that ketone, it actually turns out to be more reactive than the ester. So as soon as it forms, it's going to find more Grignard and react. So that's why we can't stop. If we ever form this, it's going to sop up any remaining Grignard reagent that's in the pot. So we have to add two because we have to take advantage of this second addition of Grignard reagent to the ketone. So then I would get this product after I deliver another CH3CH2 group, and I'd get stuck there until I quench this reaction with a little bit of acid in the second step. Okay, so the reason again that we have to add two equivalents of this reaction is that our first reaction is going to lead us to a product, ketone, which is more reactive than the starting material. So if you tried to get cute and say, well, hey, I'm only going to add one equivalent of Grignard reagent, what you would isolate is 50% of this doubly alkylated product and 50% of starting material. Okay, so that's not a very productive reaction. So what we have to do is double up on the amount of Grignard reagent so that we push this all the way to completion to make the tertiary alcohols. Okay, so we're always going to be adding 2 equivalents of Grignard reagent. One last thing that I will say here with this is that, as you might expect, this also works with alkyl lithium reagents. So if I have an alkyl lithium reagent, it also behaves like a carbon minus. Should make sense to you that that can behave in exactly the same way as the Grignard reagent. All right, as a few examples of that reaction. So let's say, for instance, I have this ester, and I decide to react it with phenyl magnesium bromide. Again, I'm going to add 2 equivalents of that reagent and follow that up with an acid workup. So what this means, again, is I'm going to deliver 1 equivalent of pH minus to the carbonyl, form a tetrahedral intermediate, have those electrons come back down, spit out my OCH3 leaving group, reform a carbonyl to make a ketone, and then that ketone will undergo a second addition of the phenyl group. And so what I would get out of this, again, is going to be a tertiary alcohol where I have added 2 phenols to the carbon that used to be the carbonyl carbon. So as another example, let's look at this ester. And let's say, for instance, I decide to use allyl magnesium bromide. Again, 2 equivalents, because I can't get it to stop halfway. And then follow that up with an acid workup. So again, I'm going to deliver this allyl group. So what I really have here is this. And that's going to be my nucleophile that's going to add to the carbonyl and push the reaction forward. So what I would get out of this one is another tertiary alcohol that now has 2 of these allyl groups attached to it. So that would be my product. So again, always making tertiary alcohol products. Okay. So this is similar to the outcome that we saw with reducing esters with lithium aluminum hydride, right? Because again, we could not stop at that aldehyde intermediate because that aldehyde was also reactive, and in fact more reactive than the ester. So we would go all the way from the ester oxidation state down to the primary alcohol. Same thing is happening here with carbon-based nucleophiles. We solved the problem with the reduction using the diball reduction, right? Where we could trap that tetrahedral intermediate and prevent it from reacting further. Well, there's a similar strategy that we can use to alkylate something in the carboxylic acid ester oxidation state and get it to stop at the ketone product. That's the final reaction that we're going to talk about today. So it turns out that you can alkylate. So I think this might be the 6th reaction we're talking about. Turns out that you can actually alkylate nitriles to make ketones. So this is similar to the diball reduction in that it's going to allow us to stop at the ketone or aldehyde oxidation state without moving forward and adding another nucleophile to make alcohols. So here's what that reaction looks like. If I take a nitrile, and it doesn't really matter what the carbon group attached to that nitrile is, if I react that material with, let's say, a Grignard reagent like methyl magnesium bromide, and then I follow that reaction up with excuse me, acid and water, what I will make actually is the ketone product. So that looks a little bit weird on the surface, but let's think through what's happening. So we talked about already that we can treat that C triple bond N similar to a carbonyl, right? It can accept nucleophiles at the carbon. And so if we want to think about how this reaction might happen, I can take advantage of my methyl minus and it can add to the carbonyl and give those electrons to nitrogen. So what do I get in that case? I've now added the CH3 to the carbon that used to be the nitrile carbon. I've reduced the number of multiple bonds down to 2, and I've dumped a negative charge on that nitrogen. Okay? So this looks like a ketone, right? And in fact, if we add some acid to it along with water, so if we just think about adding acid in the second step, I will protonate that N minus, and it will become an NH, which we all know is the functional group imine. And if there's acid and water in the presence of an imine, we know that we can hydrolyze imines back to the ketone. So what have we done here? We've been able to actually do a single alkylation of the nitrile to make an imine anion, which will not add another nucleophile, because if we thought about using this C double bond N to add another nucleophile, our tetrahedral intermediate would have an N2 minus anion. Now that's just simply too unstable to form. And so we get stuck here at this imine ion until we quench the reaction. When we add acid and water, we first get an imine product, which is now hydrolyzable to a ketone. And so at the end of the day, what we fish out of here is that ketone. Okay? So this is a route that allows us to take something that's in that carboxylic acid oxidation state, namely the nitrile, and alkylate it once, but only once, to make a ketone product. And so if we want to think about a few examples of that, let's take a look at this nitrile. And let's say, what happens if I add isopropyl magnesium bromide to that, followed by acid and water? Okay? So again, after step 1, what I'll get then is the alkylation of that nitrile to make the imine anion, and I'll have delivered that isopropyl group. And then if I throw in acid and water to that, I will protonate that imine anion to make a neutral imine, which, as you guys recall, hopefully, that can be simply hydrolyzed in the presence of acid and water to the ketone. And so the product I would fish out of this sequence looks like that. So this here in the red box is actually what I would end up isolating out of that reaction. So again, it allows me to make these ketone products and stop where I don't do over alkylations. Let's do one more example. No, let me change back to my blue. All right, so if I treat this guy, I don't know, let's say ethyl magnesium bromide, followed by H plus and water, and my product's going to be carbonyl compound where I've added that ethyl group in place of the nitrile. And again, that comes from this pathway of generating the imine anion and having that hydrolyze with acid and water to the ketone. Okay? All right, so that finishes up everything that we needed to talk about for chapters 18 and 19. And so we're going to stop here, and we'll pick up on Monday after your test with a new chapter. All right, thanks everybody.